So very much welcome to the second day of the Energy Harvesting Dissemination event. And for those of you who were here yesterday, welcome back. And for new friends who have joined us today, this is a 3 days event. Every day we're having 2 hours of sessions. And today we have 4 exciting talks given to us by Matthias from Lightricity on high efficiency photovoltaic energy harvesting for IoT applications. And then Hailing from Loughborough University will talk to us about rotational energy harvesting using nonlinear dynamics for self-powered sensing. And then Denis from Ilika will speak to us about miniaturizing IoT sensors with solar batteries and energy harvesting. And Eiko from University of Freiburg will present to us, has exciting work on the thermal energy harvesting for wildlife tracking applications. And before I hand over to our first speaker, I just would like to briefly, for those of you who do not know, Energy Harvesting Network is a network of academics and industrialists in the energy harvesting sector, mostly based in the UK, but we also have, someone is controlling my slides. Sorry, can I just stay on that link for a bit? Sorry. So on the top right there, the Energy Harvesting Network website, if you're not a registered member yet, I very much welcome you to register on the network website. We currently have about 518 companies and university institutions registered on the Energy Harvesting Network website. By registering there, you'll be able to keep up to date with all the events that are being organized by the network. So every year we organize the dissemination event, and this year it's the first time we've been forced to organize online. But I think perhaps this also helps to reach out to more people outside the UK as well. So as I mentioned, in the past 9 iterations we had physical events, and this year, the 10th iteration, we're having it an online event. And it will be great to hear from you. So there's a feedback survey link here. It's a Google form link. After the event, if you can be kind enough to give us some feedback on how this event went and how any suggestions for future events, locations, or in what format you would like to see the Energy Harvesting Network events to be held, that will really help us to improve the organization of the network for the future. And in the chat box, I've posted a link, which is a copy of this PDF, including a schedule. So you're very welcome to have a copy for yourself, so you can know what's happening across these 3 days. Obviously, yesterday has already happened. And all of these sessions are recorded, so at some point in the future, it will be posted online. We're not entirely sure what platform it would be, but again, if you subscribe to the Energy Harvesting Network as a registered member, you will receive that information once we post the videos online. And just briefly about tomorrow, so we have 2 more talks tomorrow, and we'll also have a panel and audience discussion. So you're very welcome to join for tomorrow's sessions, and especially the discussion session. So it will be great to hear from all of you about your views and your opinions on what the next decade holds for energy harvesting technology. All right, so I think I'll hand over to our first speaker, Matthias from Lightricity.
Yes, thank you. So let me start sharing my screen and my slides. I'm not sure. Can you? Okay. Actually, okay, I can see.
Thank you.
Right. Okay. So I take it that you can hear me well and see the presentation.
Yes.
Yes. Okay. Thank you very much for attending this presentation, High Efficiency Photovoltaic Energy Harvesting for IoT Applications. So I'm Matthias Kauer, and work for Lightricity, an energy harvesting company based in Oxford in the UK. And I'm going to tell you today about our high efficiency PV energy harvesting technology and some applications. So to begin with, I think many of you, or probably all of you, may have seen this sort of information in one way or another, in that there's an ever-growing number of IoT devices that are being used, and so regardless of what the exact number is going to be, it's clear that it's going to continue to grow, and that it's going to sort of be very substantial in the billions, and that the majority of these devices use batteries, again, as I think we all know, and therefore obviously provides a strong motivation for the energy harvesting community to provide alternatives to as many as possible to these battery-powered devices. And so we can, I suppose, see so what problems might be caused by using disposable batteries, by sort of just sort of simply calculating the number of required battery replacements per day by the number of assets that are being monitored versus the battery lifetime. And so we can see that sort of quickly can go into the millions or possibly even higher per day, which is a sustainability problem very clearly. But it also illustrates that for larger deployments, it sort of can become an operational problem to sort of replace batteries or recharge batteries. So again, I think, as we sort of probably all know, that's obviously a strong motivation for the community and also for us to sort of look for alternative solutions to power these devices, or certainly as many as possible. So Lightricity has developed a solution for powering devices from ambient light sources. So that is our focus and our key technology that we have developed. So it's a very efficient PV energy harvesting device, generating power from ambient or indoor light sources in particular. And we think that is important because the majority of us humans unfortunately spend most of their time indoors, whether that's at work, or at home, or supermarkets, and so on, or entertainment even. And so therefore a bulk of IoT devices are actually used in sort of indoor environments with indoor lighting in all of those places, and therefore it's also reasonable to assume that the majority of IoT devices are going to be used either in indoor settings entirely, or if it's a wearable device, a body-worn device, that the user will spend the majority of their time indoors, and that this device will have to be designed around this use case. So the technology that we've developed provides power from these indoor light sources, and does so much more efficiently than technology that have been available to date. So we'll sort of come on to see exactly what that means. So that I say that's sort of our focus, and then also to provide sort of power management options around that for the user to efficiently use the device in a system. So here, in fact, is then one of our devices, and what I guess are the key features that I would like to describe now. So in the center, that's a 2 by 5 centimeter device. I'll show later some other devices that we are making and offering, but that's just one example, and the key features are the same for all of them. So in the center top, you can see perhaps the most important sort of key feature, which is these of high power per area, which is 20 to 22 microwatts per centimeter square at 200 lux. 200 lux is a dim indoor environment, like a hotel room corridor. And so the power that we provide there is between 3 and 6 times greater than alternative technologies, depending on what it is compared with. So there's some comparisons later on in the presentation. So that's clearly a significant increase in power that then is available to power applications that were not possible before with energy harvesting or light energy harvesting, or alternatively, you could make the entire system smaller and still provide the same functionality, which is relevant, for example, in wearable applications or asset tracking or some other applications. So that's sort of the key, I suppose, but there's a few others that are also very important. technology is of linear down to very low light levels in terms of power, so to 10 lux and even less. It's almost complete darkness, whereas other technologies tend to be nonlinear in terms of performance below 200 lux. It's based on an inorganic material, so it's a very stable, very long lifetime, obviously essential to realize the sort of true benefits or sustainability benefits from the energy harvesting device. Also means that it can sort of work at high temperatures and can be surface mounted, which sort of helps with integration during manufacturing. Voltage, operating voltage is around 1 volt, or obviously then can be sort of adjusted in steps of 1 volt, depending on the requirements of the system or the integrator. We'll see later that we can sort of customize the shape and size of the device, and importantly, it's fully black, which is nice for design-led applications or consumer applications, for example. So a black device tends to be sort of easier to integrate than something that's brown or reddish, for example. And yeah, as I mentioned, this is perfectly sort of suited for sort of indoor lighting conditions, whether that's LED, CCFL, or I guess even incandescent, if that's sort of still being used. So these are the key features of our technology, and I'd just like to sort of illustrate what the sort of, I guess, benefits they bring before sort of moving on to sort of some more technical details. So this just illustrates the amount of energy that's produced by 1 centimeter square of our devices. So you can see a photo there on the left at the 1000 lux, which might be as of a bright indoor conditions like in the supermarket, for example. So over 10 years to produce the same amount of energy as of over 100 coin cell batteries or a handful of AAA batteries. So that's very significant, not just in terms of the battery costs, but probably more important in terms of the environmental benefits and of the operational cost compared to sort of disposable or rechargeable battery solutions. So obviously it will enable installations in environments where it may be either very expensive or impractical to change or recharge batteries. Another way of sort of looking at that then is to look at the power output at 200 lux as mentioned before, and to compare that to other options that a technology developer or product designer may have. So you can see that in the sort of a chart on the left. Our technology produces above 20 microwatts per centimeter square at 200 lux, whereas others are between 3 and 7, or sometimes a bit more. So that depends. I think more for silicon is probably the only sort of real alternative that's available for a developer of a product. So that's been on the market for decades, I suppose, and widely used in watches or solar calculators. A very mature technology, so that may produce between 7 at most maybe 3 microwatts per centimeter square, depending on the device that's being used. So you can see there's a very big sort of step change in power per area that we provide. Crystalline silicon on the left is typically not used indoors just because it performs quite poorly. And then other technologies that are sensitized, the OPV, perovskites perhaps, so it depends very much on the technology. So there's some research results that are sort of above the values shown here, but they're still below the 20 microwatts per centimeter square, I believe, that we sort of have achieved in production already. So that sort of power per area corresponds to a sort of 30 to 35% PV cell efficiency indoors under the indoor lighting conditions, which is obviously so very high and sort of very useful and to power a wide range of IoT applications. And so as mentioned, that is linear with a light level under sort of a wide range of indoor lighting conditions, down from 10 lux to well above 1000 lux. So you can see sort of typical lighting conditions and sort of the lux values that they correspond to in the table on the right. So typically in homes would be designed around 200 to 400 lux, and offices or commercial environments somewhat brighter depending on the exact use case. So these are the key benefits around power. So if we move on to then sort of see how would that device be used. So obviously, so we provide a sort of key part of the solution. Our energy harvesting device provide a key part of the solution, but so obviously it has to sort of go into either a sensor node or some other system. So I just wanted to show that this slide again, which many of you will be familiar with, a wireless sensor node, to just to recap, I suppose, on the sort of other blocks that usually will be required to make an entire system. So there's the energy harvesting device, some power management typically, and typically a storage device and a battery perhaps, or a supercapacitor to provide peak power and sort of bridge time during periods of darkness in the case of PV harvesting. And then there's a microcontroller, typically wireless module, and sensor modules. And I think it's important to sort of recognize there that obviously so we've made very good sort of progress on energy harvesting to provide more power to the system, but also there's been very good progress being made in all of these other areas, in fact. So whether that's on F modules, so lower power radios and protocols like LoRa and the BLE, ultra wideband, where the power and energy required to send a bit of information continues to go down. That means that data can be sent more frequently over long distances, obviously expanding the applicability of energy harvesting. And likewise, still good progress being made on MCUs with the operating voltage coming down, quiescent currents coming down, and so on. Likewise for sensors, sensor voltages coming down, and power consumption. And of course, we'll have a talk later today on solid-state batteries by Ilika. So again, so some very good advances being made on batteries and rechargeable storage technologies too. So we think there's sort of strong opportunities there that so result from all of these technical advances, including sort of ours that we are contributing on light energy harvesting. So here then is a range of devices just to bring to life a bit more what the possibilities then are in terms of utilizing this technology. So you can see that we can manufacture and fabricate those in a quite wide range of sizes, from so below a centimeter square on the left to a few centimeters square in the middle, and so that means that we can address a wide range of applications, whether that's some asset tracking devices where, as mentioned, it may be desirable to have something that's quite small and maybe doesn't require so much power, or a building automation sensor which may require a bit more power because it has a gas sensor, for example. So we can sort of address these requirements with the quite small devices, which will sort of increase the attractiveness of energy harvesting to system integrators. You can see there's a semicircular device there, just to illustrate that we can customize the sort of size and the shape of the device to fit into particular product designs, which is particularly relevant for wearables, where every product design is different, and the design obviously is very important for the overall product. On the right-hand side, you can then sort of see how that might be integrated with electronics. So as shown earlier, typically will require power management and a rechargeable storage device to provide a regulated output voltage for the sensor. So the sort of small board that's shown there in the picture on the right is a design that we have developed that integrates all of those elements. So one of our small energy harvesting solar cells, some power management, and a rechargeable battery, actually in this case, to provide a regulated output voltage at 1.8 or 3 volt. That's configurable, and then to provide a continuous power output of up to 50 microwatts and up to 100 milliwatt peak output, which is obviously sort of a quite substantial, and which will be sufficient for a range of wireless radios, and also for a wide range of sensors to provide peak power to those devices. So moving on, so here is some further detail on the sort of technology features of one of our devices. So it's a 2 centimeter square device, or just over 2 centimeter square device that we are showing here. So in this case, a 1 volt design, and you can see the the technical data on the right there, so over 22 or 22.1 microwatts per centimeter square under LED spectrum that both us internally and also other users, companies and research institutions have benchmarked and sort of compared. So obviously very comfortable with the numbers that we are showing there. And I just wanted to sort of say again that the sort of module size, shape, thickness, configuration can be tailored to the application. Yeah, as I said before, also it sort of operates at high temperatures in excess to 100 degrees, which is useful, for example, for industrial applications or other applications where wide the temperature range is desired. So here then it's just a few sort of broad application areas before moving on to some specific examples. Again, I think many of you will probably be familiar with these potential applications for energy harvesting, in fact, more generally speaking, but I just wanted to illustrate specifically what our light energy harvesting technology will enable in those application examples. So for example, on the top left, there are retail applications around electronic shelf labels. So these are small displays, typically e-paper or e-ink displays on shelves that will be wirelessly updated to show price and product information. And so yeah, it's obviously desirable to have those powered by energy harvesting rather than batteries. But one of the reasons why that hasn't happened is that actually the power consumption of the display plus wire solution is relatively significant, or certainly beyond what the many energy harvesting capability the technologies have been capable of. So we can offer more power there than was available before. There are also logistics application in retail as well during their transport. For example, or warehousing. Moving on to industrial IoT, obviously we had already some sort of great examples and use cases being described yesterday by Martin Bragg from Honeywell. There are sort of a few others in sort of stock management and tracking, for example, in warehouses or vertical farming, where one wants to control the environment very precisely. And again, so we can provide power to self-powered trackers, for example, that sort of can be deployed in these use cases in large quantities, and then so really bringing to life the operational benefit of not having to replace or recharge batteries. Bottom left, smart city applications, so many use cases there around energy efficient buildings, clearly whether that's self-powered environmental gas sensors, temperature sensors, and so on, but there are also applications in smart parking, for example, or environmental sensing. And then there's sort of a whole host of other applications in smart cards for payment and access, wearables, for example, medical devices, consumer. But just like to move on then, and so just to show so some concrete case studies of how our device is being used already, and then some innovation projects that we've been working on to explore new use cases in these areas, and actually also some outside of these areas. So here's an example of how our device is being used in a watch product. So on the right you can see the watch, so it's I guess that's a classic design, and with a sort of an analog dial, but the customer or the watch manufacturer wanted an ability to power a Bluetooth chip in that case to provide connectivity to a smartphone for interacting with the watch as is expected by many customers, but at the same time obviously didn't want to compromise on the particular design language that they have adopted for their product, and so for that reason they wanted us to make these extremely small devices that you can sort of see on the left there in a very peculiar shape to sort of fit into that watch, and nevertheless to provide enough power to a Bluetooth chip, which is what this is being used for. So you can see there really that the high power per area and the ability to customize the shape is sort of really key for realizing this application there. And you can imagine there are other applications in wearables, obviously other wearable devices or watches where that can be equally of benefit, for example, to power a wider range of sensors, like health sensors, for example, or to include better displays than are currently available, while still obviously maintaining most of the, if not all of the sort of area on the dial for display or other features on the watch, rather than sort of utilizing all of that area for solar cells. So that's one sort of a key application for light energy harvesting, and obviously has been for a long time. But yeah, the high power per area sort of really enables sort of a wider range of product options than in the past, and so I think we'll sort of see many more of those in the future. Then I think it's also worth sort of going into some other examples as to see what other potential use cases can we address that perhaps weren't possible before. So just like to present a few examples that we've been working on as very different industries, different requirements specifically, but all requiring more power than was available traditionally from light energy harvesting devices. So this example here is a very interesting one, actually, in that it relates to tracking of train assets or rail assets in a railway application. So it's a project that we're running with a Network Rail in the UK, the compound semiconductor applications catapult, and a few sensor companies, AP Sensing and Pireus. And the concept there is that Network Rail already has a fiber deployed alongside most of its tracks. So track infrastructure, and that's being used for communications at the moment, but they see that also as a route for deploying sensors to monitor condition of the tracks, for example, whether that's temperature, ice, snow, and so on, and to obviously feed that back into their sort of data infrastructure. And so this project was developing a network of nodes that were deployed alongside these fibers, so to tens of kilometers away from the head end. So the requirement there was to power a sensor that is does not have any external power, but can communicate back over the fiber. So in fact, in this application, the communication is via sort of piezoelectric transducers that induce sort of changes on the fiber that can be picked up, or modulations on the fiber that can be picked up by a head end, let's say tens or 100 kilometers away from the location of the sensor. And you can see sort of some pictures there of the network rail trial installation that took place earlier this year, where we successfully demonstrate with the other consortium partners that we can provide power to this sort of entire sort of set of sensors that's shown in the small box there, and that we can modulate the signal that can be picked up 70 kilometers away by the sort of head end. So obviously that provides then a route for deploying sensors across a network rail infrastructure without having to provide power to each individual sensor node. So that's sort of higher value specialized application, but nevertheless sort of a very sort of interesting opportunity, where sort of the high efficiency and sort of high power provided by PV energy harvesting is really important to provide all these sort of sensors that are required in this example here. Moving on, I'd just like to show one further example. This one is from the medical sector, again, where there are, generally speaking, obviously many applications that are wearable or portable, and where it's desirable to have a means to provide power without having to worry about recharging batteries, for example. So this particular project looked at providing power to a new X-ray detection technology that's being developed at the University of Surrey and at Cheney, a X-ray company near Cambridge. And so that was then developed in collaboration with the Royal Surrey County Hospital, again to make a demonstrator that you can sort of see in the center there to provide power to the low power X-ray detector that was being developed there, and the readout electronics, and again to communicate that in this case wirelessly over Bluetooth transmission. It's again a higher value and more specialized application but you can see that there's concrete applications here where the higher power can then be used to power applications that were challenging or not possible before. And so that can be extended, for example, into this dosimetry, so monitoring of exposure of workers in environments where they may be exposed to X-ray, for example, whether that's in hospital environments or in industrial environments, where there's then the benefit, obviously, of having autonomously powered batteries for the dosimetry, real-time dosimetry. Then just one further innovation example, which is the Amanda project, so a Horizon 2020 project that's running over 3 years. And the concept there is really to bring the best of wireless sensor node technologies and building blocks that I showed before together and make something that's really small and powerful in terms of the sensing platform. So you can see the concept there. So it includes our energy harvesting device, a solid state battery from Ilika, some very low power imaging chips that are provided by EPs and very low power CO2 sensing technology that's being developed by IMEC. So really pushing what's possible today with ultra low power sensing, and then again, so for transmitting that either over Bluetooth or LoRa. So that's a very interesting project to follow. So that's obviously still going on, but some very good initial results there already, some of which are being published or have been published already. So you're really pushing what's possible there in terms of integrating best-in-class technologies. So just like to, I guess, close the presentation of examples and use cases with another case study of what may be possible in the near future. So this case study here is around real-time asset tracking, and I'll try to see whether I can play a video here, and hopefully we'll be able to see that as I speak. So what's shown here is an office or 2 offices where we have self-powered asset tracking tags. So these are entirely powered by our device from the indoor light in those offices, and you can see that we can track them as they move around in real time. So there are a couple of gateways that pick up the wireless transmission signals from these devices continuously, and then we can triangulate where they are within around 50 centimeter accuracy. And so that's, as you can see there, happening in real time, and with our device then can be perpetual. And so there are many applications that we can imagine in logistics for tracking assets in warehouses, for example, supermarkets or industrial environments, or for example in healthcare applications, again for tracking assets, or for people to facilitate health and safety, for example, social distancing. So many examples where it's beneficial to track devices and people, and so the self-powered aspect then obviously providing real benefit. So it's possible to do so without having to recharge the device or to dispose of disposable batteries. So again, I'm sure we'll see many more of these types of applications powered by energy harvesting in the future. So that concludes my presentation. So I'd like to summarize before closing. So I was able to show you the benefits of high efficiency PV energy harvesting, enabling batteryless applications, so no batteries to replace or recharge during product lifetime. We have a very high lifetime device in excess of 10 years, actually over 20 years for the cell material in terms of robustness, very high performance, reliability, a wide illumination range, therefore enabling new functionalities, reducing new footprint. I've shown you some use cases and the application examples there. Also showcasing the customization availability to fit into a wide range of products, and it's mass producible, so we can manufacture those devices to enable the uptake of energy harvesting in more and more applications in the future. Yeah, so with that, I'd like to so thank you again for listening, and I don't know if you have any questions now, whether you'll be able to to us though. So if not, you can always contact us via our website if you have any questions or inquiries. So thank you very much.
Thank you, Matthias. And are there any questions from the audience? Yes, Rami?
Yes, hello, good morning. Thank you very much, Matthias, for the presentation. My apologies if I might have missed it in the beginning, but can you explain what is the architecture of your PV cell?
Sure, yeah. Yeah, so it's around a proprietary material and the manufacturing process that we have developed. So there's an inorganic semiconductor material. So I suppose for realizing high efficiency and high lifetime and to make it manufacturable, all of those elements have to come together. So the right material, the right manufacturing process flow, and the right device architecture. So there's no sort of simple or single silver bullet that sort of provides sort of the solution there, but so really all those have to come together to maintain very high efficiency. And so that's where sort of a lot of our IP resides. And so obviously sorry that I sort of can't provide sort of a lot of information there in terms of the details of that, but I hope you were able to see at least that it sort of is very efficient, obviously, and so we can sort of then sort of realize the use cases that I was showing.
Yeah. Understand. So would you say it's a hybrid organic and inorganic material structure?
No, sorry, it's completely inorganic. So no, it's not a hybrid structure. So it's completely inorganic material, which and then enables the sort of temperature robustness and long lifetime.
Okay. So, and sorry, last follow-up question. And so, what is the typical price of a PV cell?
Sure, that's a good question. Well, I think that sort of will depend a lot on the specification, on the volumes, and so on. Certainly, if you or anyone else has an application or so where there's interest in that, then please do get in touch via the website, and we're obviously sort of happy to discuss with you there. But yeah, they're sort of similar to other PV devices, where you find a broad range from maybe a few dollars to up to 10 or sometimes in excess of $10. So it's a wide range depending on specification and size and so on.
Thank you.
Thank you. Any other questions? Yes, Eiko?
Thank you very much for your talk. I wonder whether you are specialized on PV cell manufacturing, or are you also doing custom ICs for your products, or are you using, for example, just standard components for the energy harvesting part, like I know for solar cells, some components from Texas Instruments, for example, or you're custom defining your ICs there?
That's a good question. Yeah, so our core technology is, and in terms of manufacturing, is around the PV device that we offer as a component. And then in terms of integration, we do have, for example, the power supply that I showed earlier that combines off-the-shelf components for power management and rechargeable storage. So we don't develop our own ICs, but we do have know-how in terms of power management architectures and so on that we can offer to customers or integrators if they require that. That's because not all integrators have the sort of capability or desire to learn how to make ultra-low power designs. So we sort of offer both, depending on what the customers or integrators would like to have from us, basically.
Okay, thanks.
Thank you very much. Okay, maybe just one last question. Yeah.
Hi, thank you very much. My question is, can they also be used outdoors?
Yes, yeah, sure. Yeah, they can be used outdoors, and in fact, yeah, obviously, our wearables customers sort of use them sort of indoors and outdoors, depending on where the sort of the customer is with their device. So outdoors, generally speaking, the amount of power that's produced is so great, orders of magnitude greater, just because of this high illumination level. that it's not an issue for system design. So the system design for a wearable device would be designed around 200 lux, for example, a use case, and then outdoors it's obviously will produce an excess of power, but it's still very efficient under outdoor applications as well, clearly. What we typically say is if the customer has an application that's purely outdoors, so if we think of outdoor power generation, then obviously there's crystalline silicon that's available, that's sort of scaled up and widely available. So if there's sort of a pure outdoor application for outdoor power generation, then perhaps there are other technologies which may be better, but that depends then on a sort of case-by-case basis. But certainly if it's a hybrid application like a wearable device, yeah, our technology would still be the best choice just because it performs so well in indoor conditions where people will be most of the time.
All right. Thank you very much, Matthias. Thank you.
Yep, thank you.
Just mindful of time, I think we need to move on to the second presentation. Thank you, Matthias, again. And our second presentation is from Dr. Hailing Fu from Loughborough University. Hailing, are you ready?
Yes, I'm ready. Just to open my document. I'm not sure how to do this sharing. I'm trying now. Sorry about that.
No worries. On the bottom right side, the share content button. And then if you click on share application /screen.
Okay, I see. Not share files. Application screen.
Better to do share application /screen. That's quicker. Share files, it'll try to upload the file.
Okay, got it. Thank you for the introduction. Thank you. Good morning, everyone. My name is Hailing Fu. I'm a lecturer in electromechanical systems in Loughborough University. Today, I would like to talk about my research on rotational energy harvesting using nonlinear dynamics for self-powered sensing. So a little bit about the background. I think lots of our presenters has discussed a lot on the background for energy harvesting, but I would like to briefly talk about it from a different perspective. So we know the Moore's law from a semiconductor industry. So the number of transistors and the resistors on a chip doubles every 2 years. And we just saw the figure from Matthias' presentation. So in the next 10 to 20 years, we're going to enter an area in the Internet of Things. And in that area, we're going to have hundreds of millions or even trillions of electronic devices. So let's envision what electronic devices we have in that area. So we would have millions of cloud stations online for storage and computing. We will also have billions of mobile devices like the mobile phone or iPad that we use in our daily life. And in addition to that, we will also have hundreds of billions or even trillions of sensors, such as wearable or implantable devices or sensors to monitor machine operation and critical infrastructures. With normally for those sensors, they are powered by batteries, which has a limited lifetime. So it would be a great challenge to replace or recharge those batteries when they have such a large number of sensors. So the solution is we can either reduce the power consumption of those sensors, or we can find alternative power sources. So there are lots of different energy sources in our daily life, and we can use such energy harvesting units to convert those energy sources into electricity to achieve energy autonomous sensing. Well, for different energy sources, there are lots of research has been done, but there is one type of energy source which is less developed, which is about the rotational energy harvesting. We know for rotational motion, they are heavily used in large power generation like hydraulic or wind power generation, but for small scale, like wearable devices or implanted devices, those energy sources are less developed. And there are actually lots of situations where we can get rotational energy sources, like the wristwatches, footwear, and also automotive applications. And if we look at power generation capability, they vary significantly from microwatts to million watts. In my research or in energy harvesting, we focus on energy density lower than 1 milliwatts, and we collect those energy using miniaturized energy harvesters for self-powered sensing applications. So that's the background for energy harvesting. Now let me talk about my research on rotational energy harvesting using different devices that we developed. So the first one is an airflow energy harvesting device using microturbine and piezoelectric transduction. So from this figure, you can briefly have an idea about the dimensions of the device. And for this system, the airflow enters the harvester from the side, and then the rotor is driven by airflow. So on the rear of this rotor, there's one magnet mounted on the surface, and the piezoelectric beam is mounted on the casing. So on the tip of this piezoelectric beam, there's another tip magnet. So these two magnets build a coupled magnetic force. So each time this rotor passing by this tip magnet, there will be a magnetic force applied on the beam. So the beam is plugged. And when this magnet rotates away, the beam is released. So this type of motion is generated. So it's plugged at this moment, and then the beam can vibrate freely for a few cycles before the next plugging force applied again. So we call this mechanism as frequency up conversion. The advantage of this one is that no matter how low the frequency of the rotor is, the beam can always operate at its resonant frequency. So in that case, we can address the problem of off resonance of typical vibration energy harvesters. So we tested the device in a wind tunnel for different wind speeds. It reaches a good amount of power output, but there are critical issues that we identified. So for those devices, for airflow energy harvesting, we always consider the startup speed, which is the lowest speed that can make the rotor rotate. So in this design, because we have such a concentrated force in the design, we have a pretty large startup speed. This is the first problem. The second problem is that when we increase the wind speed, instead of having increased output power, there is a power fluctuation, and the power reduces at high speed, which is not ideal. So in the later research, we addressed these two issues using different mechanisms. So the first work we did is to address the cut-in speed problem. So previously, the driving magnet is fixed at the edge of the rotor, but in the new design, we introduced a microspring to adjust the position of this driving magnet along the radius direction. So we know when there is a rotation, there will be centrifugal force generated. And when the speed is increased, the centrifugal force increases as well. So the gap, the length of the spring can be adjusted for different rotating speeds, and the rotating speed is correlated to the wind speed. So for this design, at low frequency, low airflow speed, or when everything is static, the gap between this tip magnet and this driving magnet is quite large. But when the rotor is driven by airflow and rotates at high speeds, the centrifugal force will push this driving magnet to the edge, which decreases the gap between these magnets, and the force is increased. So this mechanism is called self-regulating mechanism. And we established the theoretical model, including the magnetic force, the piezoelectric transduction, and also the self-regulating mechanism. So, and we optimized the spring using this model. And the critical factor in this design is the spring constant. How can we achieve an appropriate spring constant to achieve the aim that we are targeting at? So in this case, we manufacture such a microspring. We use titanium foil and laser machining to cut this microspring. So these are the dimensions. And then we mount the spring on the rotor. So this spring will deform in this direction, and it is driven by the centrifugal force. So eventually, this is the energy harvester we assembled, and we tested also in the wind tunnel. So for this design, the cutting speed is much lower, and the output power is increased significantly. And we can see that at high airflow speed, the fluctuation issue is addressed to some extent. But until now, we haven't understand why there's a power fluctuation at high rotational speed. So later on, we used the theoretical model we established to understand what is going on at high frequencies. So we tried different configurations of this magnet piezo beam orientations and investigate the best configuration for such a method. So in those graphs, it shows the tip velocity of the beam, the magnetic force applied on the beam, and also the input power from the rotor to the beam. So eventually we identified this one is the best one in our case. And in terms of the power fluctuation, we can look at this figure. If the rotational speed is very low, we have enough time for the beam to ring down. But if the frequency of rotation is too high, the beam is not fully ringed down, and there's another plucking force appeared. So there will be phase mismatching between the beam vibration and the input driving magnetic force. And those phase mismatching will generate such power fluctuation problems. So this is the reason why we have frequency output power fluctuation at high frequencies. And we identified the relationship between the rotating frequency and the fluctuation frequency using the theoretical model. And eventually, we found an equation to determine the upper limit of this excitation frequency before you have significant power loss. And from this equation, we can find that if you increase the quality factor of the system, if you decrease the quality factor of the system, the upper limit of this operating frequency can be enhanced. So eventually, what we need to do is to decrease the quality factor by that, we need to increase the system damping. And we know for system damping, there are two factors. One is mechanical, the other is electrical. So I tried both methods to solve this frequent output power fluctuation problem. So in the first case, we tried mechanical nonlinear dynamics. In this case, we introduced bistability into the system. The design is quite simple. What we did is we introduced another fixed magnet on the top of this tip magnet. So this fixed magnet is on the same casing as the beam. So there's no relative motion between these two parts. And the magnetic force between those magnets are repulsive. So ideally, the forces are in the vertical axis, but there are always some mismatching, or when the beam is vibrating, there are always horizontal components generated on the beam. So this horizontal component will push the beam either forward or backward. So we have two stable positions for this piezoelectric beam. So that's what we call bistability. And it will be the same. So the beam will eventually driven by this driving magnet. So each time this driving magnet passes by the tip magnet, there will be energy injected into the beam. And for bistable systems, there are different operation modes, like we show here. So this is the interval, this is chaotic interval oscillation, and this is periodic interval oscillation. So this is the ideal case where we have large beam vibration velocity and displacement. And if we look at the beam vibration again, so after one plugging, the beam can oscillate in this interval oscillation for a few cycles before it goes to the interval oscillation with much smaller vibration amplitudes. So this effect can avoid those phase mismatching at this moment. So we compared such a bistable system with a system without bistability, and we can see the advantage. And then we tested everything using this setup. We can see the bistable motion from this harvester design. And if we look at this figure, if we look at the black curve, we can see a much higher increase in the output power and relatively lower power oscillation. So like I mentioned, this is the mechanical damping work, and then we tried to increase the electrical damping as well. So essentially, we would like to get more power from the beam. So we used this SSHI method, synchronized switch harvesting on inductor. This is a well-developed method for power management for energy harvesters. So compared to a typical bridge rectifier, for this one, it include another synchronized switch using inductors. So what happens here is at the extreme of the beam vibration, the switch will be on, and the voltage on this piezo beam will be reversed. So by doing that, the conversion efficiency can be increased significantly. So this is the typical diagram for this interface. I'm not gonna introduce the detail for this one now. So we actually built the fully coupled electromechanical nonlinear model for this energy harvester design. So we have the magnetic force calculation, we have the mechanical part for the piezoelectric beam, the electrical part as well, and then we also include the SSHI operation in MATLAB, and this is the storage part for the energy harvester. So using this model, we can understand the dynamics of the system in time. I'm not going to introduce all the modules in detail, but this module can be shared if you need it, if you are interested in this one. Let's look at some of the results. So here we do a comparison between a system without bistability and without the SSHI interface. And these figures are the harvester with both of them. We can see in terms of the displacement, the displacement, because of bistability, there's a little bit increase in displacement. And after each plucking, the bistable one will be static very quickly, but this one will take a more long time. In terms of the output voltage, the bistable and SSHI one have a much higher output voltage. So these are the advantage of the method we proposed. And if you can, well, these are the simulation results and these are the experimental results. If you compare these two, it shows our theoretical model is very precise to predict the dynamics of the system in time. So in these figures, we evaluate the output power for different plucking frequency or rotating frequency and different load resistance. We can see that the power fluctuation issue is addressed significantly and the power is also increased. These are the final results, and we compared the different configurations, and the one we proposed in this slide has the best performance. So in terms of the output power, it enhanced almost 5 times, which is a significant enhancement. So eventually we tried a self-powered sensing application. So we used a commercial available wireless sensor node called Telus B. So there are microcontrollers, ZigBee modules, and sensors embedded on this board. And this is the power management board we designed. So if we look at the results, we have a storage capacitor which can reach the voltage above 7 volts. And when it reaches the threshold, the sensor node will be on. And so you can see the discharge of the capacitor. So 3 transmissions is complete when the storage capacitor is discharged. And so essentially we can get the temperature and humidity readings from this board. So we run the whole thing for several hours. It works pretty well. And the last application I would like to introduce briefly is the application for wind turbine. So this is a collaboration with ETH Zurich. We actually got the operational data for the turbine tower. So if we look at these figures, we have wind speed in the horizontal axis, and for the vertical axis, they are peak acceleration amplitudes and frequency. Well, in terms of the characteristics, the motion is extremely low frequency, and the amplitude is extremely low as well, if we think about the motion of the tower. So this is a critical challenge for energy harvesting. And we proposed a design using rolling magnet, using this rotary translational motion. So we have a rolling magnet inside a casing, and we use electromagnetic transduction in this case, so 2 coils above the casing. And here we have 2 tethering magnets to control the motion of the rolling magnet. We would like to make sure the magnetic flux within the coil is always maximum at these 2 locations. And by using these tethering magnets, we can create two stable positions for the harvester as well. So it's also a bistable energy harvester, and we calculated the potential well for the rolling magnet. We can clearly see these two stable positions. And then we did a frequency sweep to see the performance of the harvester at the frequency range we identified. And we can see the harvester has a good performance over a wide frequency range with good output power. So that's pretty much about the presentation today. In conclusion, today I present several work on rotational energy harvesting in terms of frequency of conversion, self-regulation, and bistability. We built models for coupled electromechanical systems, and we have applications for wind turbine as well. Thank you for your attention. Do you have any questions?
Thank you, Harling. If there are any quick questions from the audience? No. If maybe just cautious, mindful of time. Maybe if anyone has any questions, can find Harling afterwards. Is that okay?
Yeah. Thanks.
Yeah, thank you very much.
Thank you.
So just mindful of time, we'll move on to the next presentation. Thank you, Harling, once again. So our next presenter is Denis from Ilika, who will talk to us about the development of solid-state batteries that Ilika has been working on. Denis, you ready?
Thank you. Yeah. Can you see?
Perfect.
Thank you. Can you see my screen? Okay. Well, good morning, all. I hope you can see my screen. I'm trying to open my video as well. There you go. Okay. So thank you for the invitation to talk at this great event. My name is Denis Pasero. I'm product manager at Ilika. I'm talking to you virtually from sunny Southampton in the UK. I'm going to be talking to you about how solid-state batteries may help you in the design of IoT sensors. Actually, we have two solid-state battery programs at Ilika. The Stereax range of products is at the milliwatt-hour level. So these are miniature batteries that we integrate in medical, implantable, but also industrial IoT sensor. And this is what I'm going to be concentrating on today. But we also make much larger cells at the watt-hour level, initially from a pull from the EV, electric vehicle industry, but also applications in consumer electronics, the aerospace and the military. So the benefits of combining energy harvesting components in an IoT sensor should be well understood by this community, I guess. By harvesting energy from the environment, either solar, vibration, or thermal, even RF, or we've seen by rotational energy just now, you can increase the life of a device. You may not have to replace batteries as often. You can miniaturize the device as well, as long as the energy harvesting component itself is of small size. You may even go to the extent of not having any batteries at all. So you can design little circuitries as shown in this schematic top left here, which I borrowed from NSS. A simple design of a sensor, those measurements, and wirelessly send the data to an edge node or a gate and then to the cloud. The advantages of such a design is it's wireless, so it's not cabled, so you can place the device in a hard to reach place as well, and it's autonomous, of course, because the nature of the harvesting and the battery. The point about not having any battery at all is interesting. Is the ultimate aim, I guess, of energy harvesting. But due to the intermittent nature of energy harvesting, for example, at night when you use solar energy, you will, in a lot of use cases, need a energy storage component in your device, which could be a battery. A few examples at the bottom of this slide of demonstrators we built with some of our batteries, here showing examples using solar energy. So you can see we are using often the Lightricity panels, which I can confirm are of excellent efficiency. And you can make very small size sensing devices here, sensing temperature, for example, and transmit that through Bluetooth. Just going back a couple of slides on what the solid state battery is. Well, it really is a lithium-ion battery, but made with different materials and different processes. So the material, the key difference is the use of fully solid materials, including the electrolyte. So you don't have a battery that with toxic materials and potentially explode. They are designed using semiconductor type equipment, evaporators, spectras. We deposit our batteries on 6-inch wafers at the moment, and you can see a wafer on the right-hand side, and all the little rectangles are cells. They are patterned using conventional semiconductor masking and patterning techniques, so you can have all sizes and shapes that you could think of, and also you can miniaturize them. So these batteries bring a set of advantages in terms of cycle life, power rating, and so forth. And I'll go into a little bit more about this now. Why would you want to consider a solid-state battery as an energy component in your device, since you do have several alternatives, including some rather cheap cone cells, lithium-ion cone cells. At the bottom of this slide, I point out that this is a new technology. Even at volume, we don't expect those batteries to be at less than $10. It could be several tens of dollars, depending on the size. So you really need to align your requirements with what a solid-state battery uniquely provides. And so a list of benefits here. They can be operating to much higher temperature than alternatives. 150 degrees is what we can do right now. They can be made ultra thin, so 150 micron is what we can do right now, but we can go lower as well. And even though they are very small, I showed you in the previous slide back here, top right, this is one of our batteries. Even though they're quite small, they have fast charging and high power capability. And I'll show you that they can power wireless communication. And I've also mentioned that they are safe. They won't explode. So this conversation today is about trying to make you understand what these benefits are and whether they fit with your requirements. I'll give you a few examples of deployments and development programs. The first one, which was funded by Innovate UK with our partners, Professor Yushi and Yuja, initially at Chester. Of course, Yuja is one of the organizers of this event. The idea here was to design an autonomous sensor which could be very thin and placed on wind turbines, measuring the vibration spectrum of a vibrating blade in order to get a signature of a potential failure, or cracks, effect of rain, thunder, or even icing on the blade itself. So we developed this prototype with our partners, which included 2 Chinese companies, and we demonstrated it in a trial at the ORE in the UK, the Offshore Renewable Catapult, and show that this device, which can be placed on the smart composite material that our partners were developing, can read the signature of the blade itself and transmit it to a gateway elsewhere. So that was a lovely demonstration. Matthias earlier mentioned another project that we have in common. In general, application within embedded electronic, whether it's asset tagging, smart electronic cards like this one, shelf display, could be a good fit. So most of them require ultra thin components. It could be a good fit as long as the price point is acceptable. But again, this Amanda project, which is a Horizon 2020 project, is well underway and going very well with our partners, including Lightricity here. I won't give you much more details on this, since Matthias mentioned this already. An application that makes the most of the temperature resistance of such batteries is, for example, in the semiconductor industry, where sensing inside deposition chambers takes place at temperatures from 150, even higher. So here you need to have electronics that can resist this type of hostile environment. It's in vacuum as well, and being ultra thin. So we place electronics on wafers, like you can see here in the middle. There are batteries, and these are placed in this environment to make measurements about the stability of the deposition environment in those chambers. So we have a series of products, and this one is going to be developed next year, possibly a best fit for IoT application. So it's a very thin device. So it's less than 1 millimeter thick. It's about 1.3 by 1.3 centimeters, if I remember rightly. Provide 2 milliamp hours and uniquely will provide operation at these temperatures. So in an IoT, in industrial IoT context, this is a context where you really need to sense, to make measurements really near to a piece of machinery that gets hot. So that's the unique aspect of the technology here. Okay, so now a few slides on you've got a solid-state battery in your hand, and you're thinking of designing it in your product. How can you do that? What are the considerations you've got in mind in your product design? First of all, you'll be thinking about how much space you've got available, size, and form factor. The advantage of this technology through its patterning techniques is that you can miniaturize it. You can miniaturize the batteries from centimeter squared scale to millimeter scale. I'm going to try something now. I've got in my hand, if you all look at the very small window when you can see my video, is another device. So it's a small window, and I've got a very small device in my hand, which is not more than 2 centimeters long and less than 1 centimeter in diameter. This is how small we can make circuitry, including batteries inside. So this is a little medical device prototype. But this is really how small we can make them. I don't know if that went well on the camera, but this is just hot off the press, if you like. We can customize shapes, so we can make them long and thin, small cubes, interesting shapes. We can create rings out of them. So this could be interesting for you. And the very low thickness of this battery can also be very important. Actually, when we make the battery, when we deposit them, deposit it on a substrate, which is quite thick already. It's 650 micron thick, or more or less. So you lose a lot of energy density because the active battery is really the layer at the top in red. But thankfully, there are some very common semiconductor industry thinning technique, and you can very much reduce the thickness of the full device, as I said before, to 150 micron right now, and we're exploring 100 micron in the future. So you get very thin devices if it's important for you. Okay, So the second consideration will often be, all right, but can this battery really provide the energy and power required in my use case? So we have a roadmap of increasing energy density by doing things like thinning the substrate more, increasing the thickness of the cathode. So we will have several products over the next few years with increasing energy density, which may fit your requirement. And what we actually do is we also stack those batteries. So top right here, this is a stack of 6 cells on top of each other, and the whole stack is actually still less than 1 millimeter thick. But again, going back to power requirements, such a small battery, can it provide enough power for me? Well, they have high power capability, very interestingly. And so even with such small batteries, you can see that a peak continuous and peak current of some milliamps can be provided, as exemplified here by 3 pulses required for BLE transmission. So yeah, this is adaptable. You can change size, you can change the number of stacks, but you can provide high power nonetheless. Then how do you mount these batteries on your device? Our vision is that our solid-state batteries are not an add-on, a large bulky device that you with a big holder that takes a lot of space on your PCB. We intend those batteries to be considered just like another IC, direct pick and place. You don't need a battery holder. We are exploring many different ways that these batteries can be assembled. Right now, we can use conductive epoxy or wire bonding, but we're looking at laser welding and other ways of connecting the batteries, which is a departure from what common cells, for example, would require. They can be provided as a bare die, so there's a bare die here on the top right, or within an hermetic sealing package, and that increases cycle life, for example, or temperature resistance, if you have the volume available. There was a question earlier on power management, and these batteries, like all batteries, need care in terms of and protection in terms of over and under voltages in particular. Thankfully, there are already off-the-shelf components which are ultra-low power, so they fit very well with the size of our batteries and their capacity, from TI, from ADI, or even our partners EPs in Belgium. And they very efficiently also convert the power, the voltage range of our batteries, which is 3 to 4, to a useful voltage. For example, if your electronics requires 0.9 or 1.8 volts. Some other partners or customers we work with sometimes prefer to design in their own ASIC, much more expensive, so not necessarily always the case in the IoT world, much more in the medical world where we also work a lot. And here I can recommend the Swiss company Microdual, which makes very appropriate ultra-low power ASIC for this industry. Then, of course, the remit of using energy harvesting is to increase the life of a device. You would not need, as Matthias showed earlier, to change the batteries every couple of years. And so these are long life batteries, but interestingly, in the energy harvesting IoT world, these are batteries that are not fully charged and discharged every day. So this slide is heavily medical or medtech focused in a way, but the message is still the same. You can achieve extremely long cycle life by creating an energy budget that does not require full depth of discharge every time. And this little curve is a guide to the eye to showing you that by charging through energy harvesting, which will be low recharge, many thousands of low recharge over the life of the device, you can use this battery. So we have many graphics like this, and we have electronic specialists in the company. We can very much guide you to what kind of battery would fit the balance of requirements you've got from cycle life to energy and volume. Then there is the fact that energy harvesting, as well as being intermittent, some type of energy sources will also be low power. So if you need to efficiently store this energy when the harvested energy is not available, again, at night, for example, you need a component which may store this energy very efficiently, as in it should not have a high leakage current. And solid-state batteries are excellent in that respect. They really only leak nanoamp of current, so you don't lose the energy that you've provided by the harvested energy quite so much as some other components, in fact. How do you charge a solid-state battery? Well, energy harvesting is great. It works very well, and we've demonstrated that in several projects which I've already mentioned. Again, a bit of a medtech angle here, but you can also recharge them wirelessly through various type of RF and magnetic and ultrasound type of charging techniques. What's important also, at least in this sector, but in general, is that if you want to recharge your battery fast, you will know from charging your mobile phone at night that they heat up. So you really want to decrease the temperature gradient as you charge the batteries, and those batteries don't really heat up very much. And I guess when people talk about solid-state batteries, one of the main attractions is that of safety. Again, they won't explode, there won't be any gas creation, and the batteries won't swell and explode. So this is another aspect, and we are very much looking at some of the biocompatibility as well in some markets. Okay, so we are based in Southampton. We have a pilot line which allows us to provide evaluation samples to our partners. We are also working with partners who want to customize batteries for different shapes, different sizes, different energy requirement in general. We can do that already using our pilot line in Southampton. We also help them prototyping, getting a few tens, maybe hundreds of these out for testing and maybe regulation and certification. And we have plans for high volume manufacturing. So we now, earlier this year, even though COVID was really kicking in, we managed to get the investor community in the City of London to back us with a $20 million investment. Part of it will go towards creating a manufacturing line for high volume production of those batteries. It's still about 18 months away, really, but this is underway. This is to let you know that in the longer term, we can also support you with volume. I guess I'll finish my slide pack. Maybe I spoke a little fast. If you do have any questions, I've got very happy to answer them right now. Otherwise, you've got our contact details. So thank you for listening.
Yeah, thank you very much, Denis. Any questions from the audience? You can either type questions in the chat box, or you can raise your hand and unmute the microphone to ask.
There are
Maybe
some
I can
questions in the
start.
chat there, I think they were for the previous speaker.
Denis, actually, I have one question, if I may start. I see that the battery that you showed here that you say is coming out soon. It's rated 150 degrees C. Are there any plans on making batteries for an even higher temperature range?
Yeah, so not all the batteries that we're designing are for will go to 150 degrees C. So we've got several designs. On the slide here, you see a very small battery which will go into a medical device. Here, 37 degrees is okay, although they need a little bit more for assembly and so forth. 150 degrees is at the moment what we're planning for industrial applications. Then going towards 200 degrees raises some materials and chemistry issues, encapsulation issues. We'll go one step at a time. 150 is, but we've demonstrated 150 in some devices. We're optimizing those devices for longer life. So there is an element of the battery being derated as you place it in a hotter and hotter environment. And certainly at 150 degrees, the life of our current battery is smaller than if you operated it at 25 degrees C. So we're optimizing this, trying to increase the cycle life, and then we'll go after 20. We'll see what happens after 150 degrees.
Okay, thank you. Denis, I think there's a question for you in the chat box.
I'll read it out. Can Ilika work on large volume manufacturing of other systems? Do you have expertise in manufacturing automation? So I don't know what this person means about other systems. We specialize in batteries, in solid state batteries. So this is where our DNA is at the moment, and we are bringing new, fresh DNA in the company to improve our understanding of manufacturing needs, reliability, and so forth over the next year as it happens. We do not design the PMICs, for example, or all the components in a device. However, we have excellent partners and excellent electronics engineers in the company creating app notes after app notes, guiding you for that purpose. I hope this answered your question.
Thank you. Are there any other questions for? Are there any questions for Denis? Okay. There isn't. Maybe anyone with any other questions can contact Denis on the contact info on. Once again, and if we can move on to our final speaker of the day, Eiko, are you ready?
Yes, I think I'm ready.
Yeah, thank you. So our final speaker is Eiko from University of Freiburg, and I'll hand it to you. Thank you.
Okay. Let's check. Okay, I think you can see my screen now. So a warm welcome from my side also, and thank you very much to have the opportunity here to speak. Actually, my topic is a little bit aside of others, especially as a lot of people are not in the wildlife trapping application, but I will show you some basic and key ideas, especially in electrical design we have put in here. And I will demonstrate you already an application that is on the edge of being useful, which we will demonstrate with a field test we did with our system. So when we're talking about our device in wildlife tracking application, actually we are talking about a tracking device that you put as a collar on your animal, and normally you want to track the animal population, especially their habits and habitats. for example, in Germany, it's relatively useful now to get the migratory routes of the coming wolf, which we want to integrate in our cultural habitat, especially in concerning that we as human beings are taking more and more space, especially cities are growing, and you normally want to somehow keep animals in this environment. And to do this, you normally want to know especially data like location and the activity and health condition of your animals. And normally you will also get a temperature, which somehow is included in the health condition here. So when you put a collar like this on your animal, you will normally transmit all your data via satellite or some cellular networks, or also even still done is directly via a high frequency where you normally have a range of some kilometers to get the data. If you're not doing this, you normally will have to get the data that is stored in the device directly from the animal. So, especially when we're talking about wildlife, you normally do not want to touch the animal at all. The problem here is that you will have a big impact on the behavior of the animal itself, especially when you have to sedize an animal just to put a collar on. So you want to minimize especially the contact frequency, but on the other hand, if you want to have a large or a long period of time where you want to track your animal, batteries are not always the best solution, especially when you want to get data even more than 2 years. So batteries restrict somehow the use case here. And so we came up with a device approach of the thermal energy harvesting, which when you using non-moving parts is relatively robust. And of course, as a collar, it's non-invasive. And we normally would expect that your animal, especially mammals, have a constant temperature. And so you'll have to, or you will get a relatively constant energy income. So basic idea here is we can use the temperature gradient between the animal and the environment to get our energy out of this. So the question now is here, which parameters are the most important for such a system when you're using thermal energy harvesting? I already showing you here some devices we made here where you have a collar that we here have 2 thermal energy harvesting parts here, where you cold side the warm side the animal and the cold side the environment here. So basically we are relying here on TEGs. So when you're now trying to design such a system, of course you will have first to fulfill the task a normal tracker would have to fulfill, which is activity tracking, which we implemented as a step counter. And you can also measure the acceleration here, which normally will, when you leave it on, will need 600 nanoamps around that. So when you go now to a more challenging part here, the positioning tracking, it's commonly used GPS, although there might be other possibilities to track your animal, but GPS is the most common part you're going to use. So also this comes with a drawback. When you are doing active positioning tracking, you will get around 30 milliamps. And you can also, of course, put these devices in sleep and get a much lower current consumption in that sense. Also, not always necessary, but normally done is like you have to integrate a real-time clock to get an idea of which time you have and when the data is collected at the end. For wireless transmission, of course, there are also a lot of possibilities. In our case, we implemented LoRaWAN. So especially because we have a lot of flexibility of trimming our devices here, which would not be possible with other technologies like narrowband Internet of Things. So we decided here for a long range transmission, and if you want to have long range, you should somehow get to a relatively high range of up to 10 kilometers. So you will have to have a relatively high power in transmission if you want to have a reasonable amount of range here. And of course, all this energy you have to store. We here decided to store the energy not in a normal battery, but a capacitor, which means that we won't have a long-term storage, but a relatively short-term storage with the idea of having a constant energy income. So 60 millifarads is already a lot for a capacitor, so you will have to use a super cap, which will come with a drawback that you will have a relatively high leakage current. And of course, you will have to do some power management and voltage conversion to get the power out of TEG. So we are now talking about a tracking device. We ourselves also want to make measurements about the performance of the device itself. So we will have to have some additional components where we did an internal storage that have a reasonable amount of data and data points which we can store in there. And to track our performance of our thermal energy income, we also put in 4 digital temperature sensors. You already saw our temperature harvesting parts, so that we have at each harvesting part on the hot and cold side a temperature sensor to track, to be able to determine the performance of them. So of course, this all takes somehow a lot of power. And the question is now, can we run this, especially when you take a look on the positioning tracking that you have a sleep count already of 95 microamps and a leakage of our energy storage with 5 microamps. So when you're now going and combine only the sleep currents, you will see that you will get, especially due to the GPS module we're using, a sleep power of 180 microwatts. Without any optimization, we expect 100 microwatts power income. So without any optimization, you barely will get it to work. So you have to do some optimizations there. And when we're now going back to the positioning tracking, our approach is, okay, we are now putting in a high load switch with reverse blocking of the current, and we are just completely shutting down the positioning tracking, but with the drawback that we cannot use some assistant GPS data approaches, which normally improves the time it takes to get the fix. So somehow you have to store these assistance data there, and basically we derived this problem by putting this into the internal storage here. So you can cut down the GPS and you will get already in a reasonable amount, but still 1/10 of your power income is still consumed just by components that sleep. To take a look on that, what is the biggest part that is drawing our part is here definitely the capacitor leakage, which is the main drawback in the system. So when you want to improve the power outcome or the usable power here, we should work on the storage of the energy. And what we in our system still did is we have somehow a cold start capability, so which means that when our storage is completely empty, it can still be charged by our TEG system, and before anything happens there, all the components are cut off from the existing capacitor, which means that we basically are able to lower the whole power consumption in sleep mode down to only the capacitor leakage. Of course, this is not the full truth. This is a simplified version here because, of course, for the switches itself, you will have to invest some nanoamps, and especially with this electrical circuit that cuts down the whole device here, you will have to invest somewhere around 200 nanoamps, which is neglectable in components when you're talking now about these 5 microamps here. So we are now, when we're now coming to the active state, you have to take a look what tasks you can fulfill, and our power management, which we implemented in our microcontroller itself, just takes 2 components into account for deciding which task it will do. So first of all, we will measure the state of charge of our capacitor, and we will also take into account the time. As normally it's desired to only get position fix or temperature readings in minimal intervals of 7 minutes. So we all measured these activity states which were already optimized in our setup, and for a periodic wake up, which means like that the microcontroller has detected, for example, that he has to do something, he will just need around 10 microjoule. Which also includes, for example, when he detected an activity and has to increment and counter for, okay, the animal is moving at the moment. So if we want to make a state of charge check, you're still relatively low at 20 microjoule. Measurement, which means we will only measure the temperature. We will also do activity calculations and storing all the data we gathered in an internal memory. You're already going up to 80 microjoules. And now are coming the big parts here. The transmission at 40 dBm is using 8.3 millijoules. And our GPS fix will need around 450 millijoules. And basically, this is the reason why you need such a big capacitor to be able to at least store the energy for one fix here. So we now have a rough guess how much we will need in an active mode and especially in sleep mode also. So when we are now coming to the power income, which we expected to be, would be at around 100 microwatts, you have to think about the environment where our device will be. So at first sight, it looks relatively nice that we have a skin temperature of our animal of about 33 degrees. This is not a highly accurate number, but plus minus 3 degrees, it is relatively okay. And the environment, of course, also changes, but let's say for the sake of simplicity that we get 20 degrees here. But then we get a problem with our fur, which is the main difference between harvesting at a human being and an animal, because you have the highly isolating fur with a thermal resistance of up to 1.2 square meter Kelvin per watt. You will get into trouble as a typical TEG will have a very, very low thermal resistivity of 10 times less than this, which means that in the end, you will have only a very low temperature difference at a TEG because of the extremely mismatched thermal, or between of a mismatched thermal matching here. So even if you want to, you can use whichever TEG you will use, you will always have a relatively low thermal resistivity compared to the fur. And as a conclusion, you will also only get a very low temperature difference at the TEG. And normally this temperature difference then will be at around 1 to 2 Kelvin here. So to deal with these low temperature gradients at the TG, you will have you have some possibilities. You can either say, okay, I want to have a very high, still a high voltage, which normally is desired to be at 3.3 volts. Or you're saying, okay, no, I'm gonna harvest at low output voltages, but we will have higher output capability due to the lower electrical resistance in our TG. So this leads to a problem because, or at least a challenge, that if you want to have a high output capability, normally the output voltage here is very low. And especially in this scenario where you will only have 1 to 2 Kelvin temperature difference, you will get a relatively low output voltage. So we're just having here, our TG we're using here has the alpha value of 18 millivolts per Kelvin. And for TG, it's a reasonable amount of electrical resistance of 4.3 ohms. But you can already calculate that from this you will get an output voltage of around 20 to 40 millivolts when you're harvesting at the animal. And this have to be boosted up to around 3 or 4 volts. And for this, we are doing our own circuit here with a transformer on it, and we are not regulating actually the output voltage, but just transforming more or less the low output voltage to a high, low input voltage to a high output voltage, which means that the output voltage is highly dependent on the input voltage and of course the load you are putting here. So as we have a unregulated boost converter that is transforming the input voltage to the capacitor at a higher voltage here, I'm going to show you the one example of several measurements here, not with the TEG we're using, but it behaves relatively similar to in our field test later on. And what you see normally is we have our cold start capability, so still we are able to harvest a lot of energy when the capacitor, a small amount of energy when the capacitor is at a very low voltage, but when we are getting in a range that is where the capacitor already has stored quite some energy, also our charging power increases a lot. And of course, this is dependent also on the temperature difference at the TEG. And you also see it's with higher temperature gradients, peak will shift a little bit to upper voltages here. But we are doing the trick now that we normally, it's desired, of course, to stay on this peak to harvest as much energy as possible. And how do we get our system to stay on this peak is not by doing some duty cycling or step-down converters that are directly taking care of the input voltage. We are here acting at a higher level of power management, which means that we allow the whole system of staying within a certain margin of the capacitor voltage. And this margin is just controlled by the microcontroller itself by selecting its task it's gonna do. So which means that we will only withdraw that amount of energy of our capacitor that we can still say we are in a reasonable amount of efficiency, especially as our system knows the temperature gradient and the capacitor voltage here. So of course, if you want to withdraw more energy, you will stay at the very edge and then go down to the lower voltage completely to to use as much energy as possible. But if you only want to measure, you will always stay within a very small margin here. And of course, our whole system itself is driven on another voltage, which means we have a step-down converter that then is giving out a constant output voltage for the whole microcontroller and the rest of the system here. So if you are now taking a look whether this works in the field test, we now were putting together in the end 3 systems, which were 2 of them, the transparent one here with the electronics, are solely driven by our TEG system, whereas one is driven by a battery which acts as a reference, as we can also, for example, if there are outages of power income, we can still see these reasons. So let's take a look on the 2 weeks. Our system were working for 2 weeks in an area of 15,000 square meters. And our gathered data is stored internally in the NAM here, which we can read out in the end. Of course, we also have the transmission, and the nice thing was we had also a website where we had our live data that can be gathered and shown by the user. So when we take a look on a typical day of a goat, you will see that when we track our voltage of our capacitor, you will see that we will have quite a remarkable amount of different voltages we are measuring here. And this is due to our system that is power management that is based on our voltage here. And whenever you see these peaks going down, you will see that we are using here the GPS system, which very fast then empties our capacitor, and then we will need some time to get up, and in between we are of course also measuring and transmitting. Interesting here is that we have actually a day-night shift, that you can see that in the night we are having a lot of power that we can generate, and while day-wise it's way less. And in the end, we got also a mean charging power of 103 microwatts, which is a reasonable amount for such a system. But we have a non-expected difference that is quite large between day and night here. So when you're now taking a look on the charging power and the temperature you got on your microcontroller, you see on your TEGs, you see that of course it's highly dependent on the temperature difference here. And you see that if you're now taking into account at around 1.5 Kelvin, you will harvest barely anything. So when you're now taking into account the environmental temperature, which has of course some variations because this is done by measured by a far away point of a weather station here, you can say that basically the mean temperature of at the TG of 1.5 Kelvin corresponds to 28 degrees. So this is just a rough value, which means like up to 28 degrees of the temperature environment, you can still harvest something with our system. So let's come to an end. And what did we see here? We did see that we had a fluctuating input power between the night. Nevertheless, we got a very nice output power or usable power in the end of 100 microwatts. And at the moment, it seems like that lower the power consumption of our components will be challenging, especially if we want to get more transmission power. So basically, there's a lot of improvements possible at the thermal harvesting part here. But also now we are already achieving power income down to 1 Kelvin. So also our algorithm works, and even GPS is working with at least 20 times per day. And if you have some questions, you can now ask if you want.
Thank you very much, Eiko, for the amazing talk. Just mindful of time, so I just want to make an announcement first before we go to the questions. So tomorrow we have the last day of our event this year, so you're very welcome to join us tomorrow for 2 more talks and the audience and the panel discussion. And yes, any questions for Eiko? Yes, Denis?
Hi. Well, thanks for the great talk. So you've designed your device with the consideration of the space and volume you had for this particular use case. My question is, how do you see the TG industry in general going in terms of miniaturizing the size of the chips themselves, the heat and cold sinks, as a package that could be as small as possible, but still providing enough energy for most IoT use case? Do you see trends towards miniaturization?
So I think there are a lot of ongoing research in miniaturization, especially we are now using here a standard bulk TEG, but of course there are also some silicon-based etching processes that are way more smaller, but normally has a lower thermal resistance, which means you will have to have a better thermal connection. And normally, if you want to harvest at like bigger heat sources, I would say this won't be a problem. Also, their miniaturization would be possible, but if you want to harvest at very low temperature gradients, I will see some issues there, and I do not see that we have a breakthrough in that part there.
Yeah.
Yeah, so let's go on. I would say Roy.
Yes, good morning, everyone. Eiko, thank you very much for that talk. Just to say, over the last 15 years, I've had a lot of inquiries for hanging things round animals' necks to track them. And perhaps when you're getting near to commercializing a product, if you'd like to get in touch with me, I'll happily pass you the sales leads. One of them was for otters, and I'm not quite sure what the impact would be of them diving into water with your device.
Yeah, I think this device is not made for water, but that is for sure. On the cold side, environmental-wise, this would be a very nice thing, because when you're harvesting at mammals and your cold side is even wet, you will get a very or low thermal resistance of our heat sink. But for application in water itself, I know that the thermal isolation of animals in the water is even higher than on mammals on the landscape.
As I say, do get in touch with me, roy.freeland@thepetrum.com, when you want some more leads to commercialize.
Okay, thanks.
Thank you. Any other questions? And I think you can email Eiko at the email he's shown if you have any further questions. Well, Eiko, thank you very much for a really interesting talk, and thanks to all our presenters today, and thanks to everyone who has attended today. So please join me in thanking all our presenters today, and hope to see all of you tomorrow. Thank you very much. Thank you all.
Thank you.